This video looks at root loci and lead compensators. You're reminded that earlier videos have looked at what are root loci and why are they important, and how do I compute them or sketch them. This video is going to look at what happens to the root loci when you add a dynamic compensator, and in particular a lead compensator. Once you understand that, you can use any insight gained for design. First then, let's define a lead compensator. It has a generic form, a bit like this one here. You'll see K times S plus A over S plus RA, where R is between 1 and 10, and A is bigger than 0. So the pole and 0 are both in the left half plane. Now we should notice, perhaps for completeness here, that the steady state gain of this lead is given by K divided by R. So, what happens then when we look at this lead and ask what it does to the root loci? Now you remember when you looked at the lag compensation in the previous video that we said the most important thing to look at is the effect on the asymptotes. So that's what we're going to do. Now the asymptote rule that we used in the last video was this one. What happens to the centroid? Now the centroid is given by the sum of the open loop poles minus the sum of the open loop zeros equals K minus M times the centroid. Now when we add a lead, we're adding a single zero and a single pole. So what does this tell you? It tells you the excess of poles over zeros has not changed. So K minus M is the same. Now we've got a small zero and a large pole. So let's see what happens to this sum of open loop poles minus sum of open loop zeros, and let's see how much it changes. Well, the pole is minus RA, and the 0 is at A. So this is the change that we're going to get to that overall sum. So if we look at the change in the centroid position, delta C, it's going to be A minus RA over K minus M. And what do you notice? This is given by A into 1 minus R over K minus M, and this is clearly less than 0 because R is bigger than 1. So in other words, the centroid is moving to the left. So what do we know? Asymptotes are now further into the left half plane than before we added the lead. And the implication of that is we would expect that we can use a larger gain K here before we get oscillatory poles. Or indeed, in some cases, you can actually move asymptotes that were originally in the right half plane and move them into the left half plane. Now, the amount the centroid has moved left is given by this formula here. You'll notice I've taken the sign out and just written a positive number. Now, what are the consequences of all this? Lead is a high gain strategy, because by moving the asymptotes to the left, I'm enabling myself to use a larger K. But there is a downside. The steady state gain of this compensator is K over R. And so if R is large, we may find that steady state gain has got much smaller, and therefore we have bigger offsets. Let's look at some examples then. So this example, how the lead affects the allowable gain. So what we're going to do is sketch the root loci for this particular system here, G, with and without a lead compensator. So here on the left, without the lead compensator, and you'll see here's the root loci. It's got its breakaway point here not far from -1, and then the loci go slightly to the right. What happens when we add the lead? You'll see that the loci now are going this way. So whereas before the centroid was about here, around -0.5, now the centroid's here, around -1.5. So the poles have been moved further into the left half plane. And what this means is that I can use a slightly bigger K before I start getting a system which is too underdamped to be useful. Here's a different example. In this particular case, we've specifically chosen an open loop unstable system. Now if you look at the root loci here in this bottom left plot, what do you notice? You'll notice the asymptotes are in the right half plane. So we are closed loop unstable. So if you use just a simple proportional compensation, you cannot stabilize this system. What happens when we add this lead compensator? You'll notice it's going to shift the centroid to the left. Okay, it's going to shift it to the left by 1. And so you look at the root loci now, and what do you notice? The root loci comes into the left half plane, so now you can stabilize. So by pulling the asymptote centroid to the left, we've now created a scenario where we can stabilize a system which we could not stabilize before. So see observations. If the shift of the centroid is large compared to the original asymptote positions, then what the lead's going to do is it could move the asymptotes far into the left half plane. Okay? And by doing so, it could allow a significant increase in gain while retaining either closed loop stability or low oscillation. We could also move the asymptotes from the right half plane to the left half plane and therefore produce a stable closed loop where previously we had an unstable one. Now, a key observation in this is we would expect a good lead compensator to have a large change to the asymptote centroid. Otherwise we might be saying, why are we bothering? And this implies that the pole and zero of the lead compensator will not be small. So what's the point of the lead? How can we use it? Well, hopefully it's almost self-evident. Lead compensators allow us to increase gain, which means we can get a better transient performance, a faster transient performance. Alternatively, they can allow us to reduce oscillation by moving these loci further left, and or to improve stability. However, there is a downside. The steady state gain might be reduced because the pole zero ratio is R, so you're multiplying by 1 over R on the steady state gain. Now if there is no integrator, or where you need to track ramps, this reduction in gain could increase your steady state offsets, so you need to be aware of the downside of a lead. Therefore, a lead may not be suitable in the absence of an integrator or some other mechanism for recovering low frequency gain, and therefore you'll find that often a lead is used in combination with a lag or some other means of recovering steady state gain. Some numerical examples then to demonstrate the effect of a lead. Now you'll notice this differs quite a lot from the lag examples of the previous video, because here the proportional gain we can get away with to give closed loop poles with equal real and imaginary parts is about 0.6. When we use the lead, we can actually up that k, and you'll see here it's moved up to 1.6. So that demonstrates straight away the advantage of a lead. We can increase the value of this k and therefore speed up the transient performance. Similarly, for the second example, you see the original k 1.25, and when we add the lead compensator, we can up that k to 3.4. If we look at offsets to a ramp for the second example, with this particular k, that's the offset value, and with this k lead, that's the offset value, and what you will find is these two numbers are actually fairly similar, and that's because although you have lost some gain because of this third that comes from the 0, 1, the pole at 3, you've also been able to increase the k value to compensate to some extent, so actually you haven't lost as much offset as you might have expected. Let's go to MATLAB now and look at some more generic observations. So first example, we'll enter the two systems. There they are. And now we'll do the root loci. And what do you notice? So on the left here, with no lead, looks like a reasonable root loci. But when you add the lead, most important thing to notice is this value here, minus 1.5 with no lead, minus 2.5 with a lead. So you've been able to move the dominant part of the loci further into the left half plane. Now, as a consequence, we can use different k's in order to balance the real and imaginary part of the closed loop poles. There they are. And let's just look at the closed loop poles we end up with. So we're just proportional, minus 1.5 plus or minus 1.46j, so pretty balanced. But with the lead, you notice minus 2.5 plus or minus 2.48j. So we've got a much faster response. And if we look at the step responses, there we go. I should perhaps get rid of those circles now. And what do you notice? You notice with the lead, can you see it's got this faster transient, is this green one, so a much faster response, but a bigger steady state offset. And how did I get this faster response? We go over here on the right and notice the input is much more aggressive during transients. Starts at 1.6 as opposed to 0.6. What about the second example then? So here we go, we'll enter that one. There was the G and the K, and let's look at the root loci. This example had an integrator, you remember. So again, look at the key point. Where are the dominant poles? You'll see this breakaway point is somewhere around minus 1. What's the breakaway point once we've added the lead? Can you see it's nearer to minus 2.5? There's been a significant move to the left by adding this lead. And so therefore we expect that we can get much faster responses. Okay, so if we look at the k's that give us roughly equal real and imaginary parts for the closed loop poles, that were the k's there, and let's calculate the poles and see what we've got. With just proportional, minus 0.88 plus or minus 0.88j. With the lead, minus 1.86 plus or minus 1.7j. So you notice much faster poles. However, we should add a warning. There is this other pole down here, this slow mode, that has also come in. So when we overlay the closed loop responses, what do you see? With the lead, much faster transient responses, this green plot, but it has actually got this extra slow mode in this particular case, which is a bit slower to settle. And that's not something we want to look at in detail here, but what you've got is this faster transient response and a good smooth behavior. So some observations. With example 1, the root loci was improved by being moved substantially to the left. The dominant poles were at minus 2.5 instead of minus 1.5, so much faster. You had a much larger gain for use in transients, so you've got a faster rise time. You got a slightly worse steady state gain or offset, and you needed a much more aggressive input. For example 2, similar insights. The root loci were improved because they were moved much to the left. Your dominant poles were now around minus 1.9 as opposed to minus 0.9, although in this case there was also a slow pole, and you might want to look into that and see why that was the case. You were allowed a much larger gain, so again you can get a faster rise time. In this particular case, the steady state gain or offsets were similar, but once again you paid for the faster transients by using a more aggressive input. So in conclusions, we've demonstrated the impact of a lead compensator on a root loci sketch. It moves the asymptotes to the left and thus enables the use of larger compensator gains, which can be used to reduce oscillation or improve stability or improve speed. However, you're likely to get some reduction in steady state gain if you don't have an integrator, although this is compensated for by the fact that you can increase the K. This video does not cover the systematic selection of lead poles and zeros, but just allow you to see what impact it has on the root loci, so you can move on to design next.